Right, what we're going to do now is we are going to derive the formula for whole voltage in terms of the current and the thickness of the conductor. So how do I know which dimension is the thickness of my conductor? Because some people say if the current flows from here to here, so is the thickness this dimension, or is the thickness this dimension, or is the thickness this dimension? So the thickness that we're going to use in our formula is this dimension, so I'm going to call this as T. Now, how do I know which dimension to use as a thickness? The clue is to look at the direction of the magnetic field. If the magnetic field is this way, alright, so we take the dimension that is parallel to the magnetic field as my thickness. Alright, so that's how I define my thickness of my material. Now, if you remember from the previous video, we said that when Hall voltage occurs, which is the maximum voltage, what happens is the electrons which are trying to flow from left to right cannot be deflected anymore, because even though the magnetic force pushes the electrons downwards, but the electrostatic repulsion pushes it upwards. So therefore, when the electric force upwards is equal to the magnetic force downwards, then the subsequent electrons will pass straight through undeflected. So we said the equation that we must use is Fe, which is the electrostatic force, equals to the magnetic force Fb. Alright, so electrostatic force Fe is equals to the field strength times the charge. Fb equals to BQV. So we can cancel off the Q. And can you remember that field strength, electric field strength, is actually caused by the accumulation of electrons on the bottom part. So the top part has fewer electrons, so there's a PD across these two plates, not two plates, across these two sides. So therefore, the field strength is given by the whole voltage VH divided by the separation between the two sides, so equals to BV. So your VH is now equals to BVD. Now be careful that you don't cancel off this VH and this V, because this is voltage, this is speed. Alright, so they are not the same V, so you cannot cancel. Now let's go and derive another equation first before we combine both equations together. The second equation we're talking about is the current, and from your AS, if you remember, the definition of current is the rate of flow of charge. Now we are going to use one term which is may not be familiar to you. We are going to use a term called what you call it, number density, which is the number of electrons per unit volume. So N here doesn't just represent number of electrons, but it represents number of electrons per unit volume. So number of electrons per unit volume, you must multiply by volume, right, to get number of electrons. So what is the volume? Volume will be the area. So which area are we talking about? The area that we are talking about is the area that let me just shade it, this area, right? So this is times A, all right, and times the distance traveled. So your electrons are traveling from left to right, so let's call this L. So that is the distance. So A times L gives you the volume, right? A times L gives you the volume. So if your N is number of electrons per unit volume, you multiply by this volume, you get total number of electrons. So then you must times the charge of each electron to get the total charge, and then you divide by the time. So therefore, if you combine the L over T together, which is the distance traveled per unit time, you're going to get NAV Q. Alright, so this is called your drift velocity, or your speed V, and incidentally this speed here is the same speed as here. So now we can actually substitute the V inside here. So let's make the V as a subject. So V equals to I divided by N, A, and then Q. So let's substitute inside there now. So your whole voltage VH equals to B times I over NAQ times the D. Now, can you remember the A, which is this shaded area here, is actually equals to D times T. Can you see D times T? Alright, so which means to say I can simplify it further. My A can now be D times the T, right? So this is the A, then the Q. So what you're going to notice is the D can be cancelled out, and what you're going to get is the final equation, which is BI over NTQ. So that is the formula for the Hall voltage, right, in terms of the current and the thickness. And remember to remember how to derive this equation, because it is required in your syllabus that you must know how to derive this.